All right, guys, we're going to add again to our notebooks. Today, we're going to be talking about solving with absolute values on pages 5 and 6. Now, we're also going to be talking a little bit about solving compound inequalities because they sort of go hand in hand with solving absolute values. So we're going to do that as well. So if we turn to 5 and 6, and I'm just going to show you really quickly because then I want to fill everything out with you. On 5, I'm going to put our little book, so this page here, fold it in half, and then on 6, we're going to write some stuff down. So I'm just going to write it on this blank sheet of paper here so I can write it with you. Okay, so starting on 6, I first want to talk about solving compound inequalities. Okay, so if we think about the word compound, even if we don't think about it in terms of math, it kind of means the same thing as it does in English. So in English class, when we're talking about a compound sentence, we are combining two thoughts with the word and, or but. Same thing is true in math. When I talk about solving compound inequalities, we are taking two inequalities and combining them with the word and or. I guess they didn't want the but. So a compound inequality might be an and compound inequality, or it will be an or compound inequality. And we sometimes call our and inequalities the between stuff, and our or inequalities the extreme stuff. So like the real life example I always like to give here, because kind of compound inequalities are weird, is if we think about the age of teenagers. So the age that you are a teenager is between 13 and 19. So if you're any of the ages in between 13 and 19, like this, you are considered a teenager. So those are all the numbers in between. That is an and compound inequality. Versus an or compound inequality would be all of the ages that are not teenagers. So those are the extremes, because either you are younger than 13 or you are older than 19. Okay, so if I'm younger than 13, I'm like 12, 11, 10, 9, 8, or even like 12 and a half, I'm still not a teenager yet. Or I'm really old, I'm like 20 or 40 or 60, and I'm not a teenager. Okay, so the ors are the extremes, either real young or real old. Teenagers are the in-between ages. And then when we go to solve a compound inequality, we mostly solve the way we would also always solve. I'm actually going to start with an or example because it's pretty simple. You're going to see two inequalities with the word or in between, and you're just going to want to solve for each one. So like over here, if I want to solve for m, I would add the 2 on both sides, and we'd have m is less than -6, and m's all alone. Or over here, if I want to solve for m, I would multiply by 8 both sides, and so m is greater than 8. And whenever we have inequalities, we do want to graph our answers because it represents lots of numbers. Like m isn't -6. M is all the numbers that are less than -6. So on my graph, I want to put that -6, open circle because there's no line, and all the numbers that are less are to the left. And then over here, for 8, open circle, because m is not equal to 8, it's all the numbers that are bigger than 8, and all the numbers that are bigger than 8 are over to the right. And so in general, an or graph is always going to point to the extremes of the graph. It's going to point to either end, this way or that way. Now with an and inequality, you may see two inequalities with the word and in between, but generally an and inequality looks like this one here, where there's kind of three things. However, if you're trying to solve for something, then generally your letter isn't going to be alone yet. So kind of a little baby example like this would be -1 is less than 9 plus n, less than or equal to 17. And so the way that we solve this, like I always like to put my sides in when I'm solving. Whatever I do on one side, I do on the other. With an and inequality, you kind of have two equality symbols. So you should have two lines. And whatever you do to get n by itself, you kind of have to do everywhere. So you're going to end up doing it like 3 times, which sort of feels imbalanced, but it's not. Okay, so if I want to get n all by itself, I want to subtract 9. And if I do it here, I have to do it to all the things. So -1, -9 is -10. Here that adds up to 0, so n is alone. And then 17 minus 9 is 8. Oh my word, I almost made it negative. I didn't mean to. And then we want to graph that. So on my number line, we'd have -10 and 8. Open circle on 10, close circle on 8. And because and is the between numbers, hopefully it makes sense that I want to show that all of the answers for n are in between these two values, but also your inequality is saying that. It's showing that n is smaller than 8, but at the same time bigger than -10. So it has to be all this stuff in between here. So generally an and inequality is always going to connect, while an or inequality always goes opposite. Now, the reason that this is important to absolute value bars is because, well, I don't want to spoil the surprise. Let's talk about absolute values first, and then I'll show you why they kind of connect. So if you're going to remember, an absolute value kind of takes a number and makes it positive, but like the mathy definition for it is that it is the distance from 0. And the reason that it's always positive is because distance is always a positive value. So some real quick examples. If I asked you, like, what is the absolute value of 8? They would just say 8. The absolute value of -2 is 2. Here's something tricky. If I said to you, like, absolute value of 10, but then there was a negative on the outside, the absolute value of 10 is 10, but then it's kind of like being multiplied by a -1 after the fact. So this does end up being a -10, even though it kind of feels like absolute value should always be positive. Sometimes not if there's a negative involved on the outside. Another weird example that I sometimes see a goof up happen, if I have the absolute value of 7 minus 13, sometimes I'll see people change that to 7 plus 13, so 20. But absolute values are kind of like parentheses in so much as you want to do what's inside first. So you should really do 7 minus 13, which is -6, and then take the absolute value, so 6. And now those are kind of easy, so we're going to flip this on its head a bit. And if I asked you, the absolute value of something is 4, we're wondering, like, what could x have been? And hopefully you came up with x could be 4, or it could be -4. Because the absolute value of 4 is 4, absolute value of -4 is also 4. So the unique thing about absolute values and solving absolute values is we kind of always end up with 2 answers. And when there's an inequality involved, we end up with an and or an or thing. So that's kind of how this all relates. So I'm going to jump over to our book now and do a bunch more examples with you. Okay, especially because we want to talk about a process here, not just like how, like, I mean, you know, x is 4 or -4, like we just kind of thought about it, but the problems are going to get harder than this. Like, how do I actually do it? So we look at an easier one again. The absolute value of some number is 3. Well, that number could have been 3, or it could have been negative 3. And there's like a whole number line here, but I kind of feel like we don't need to do that because like we don't need to graph when it's equal, only when it's not equal. Now here's one where it gets slightly harder. And so you might think to yourself, x minus 1, absolute value of that has to be 2. And maybe you can come up with a number in your head as to what x could be. But there's another answer as well that's a little bit sneakier to find. So the way that this actually happens is if I want to solve with absolute value bars, the process that I can always follow is I take what is ever in the bars and set it equal to the outside numbers, so 2. And then I also set it equal, oh my goodness, x minus 1 equal to negative 2. So I always want to do the plus and minus of the outside number. The inside numbers always stay the same. And so when I solve over here, I'll add 1. And so x is 3. If we think about that, 3 minus 1 is 2. Absolute value of 2 is 2. Over here, when I add 1, we get that x could be negative 1. And that also works because negative 1 minus 1 is negative 2. And the absolute value of that is 2. So it kind of works out when we just make those two equations like that. Also don't need to graph again. Now, if we try one with an inequality, same idea. I want to take whatever is in the bars and then set it equal to 14. And then I want to make it negative 14 over here, but because it's an inequality, like we talked about yesterday, if I make something negative, it feels right that I should switch that sign. So now it's going to be less. So we don't switch the first one because we didn't make it negative, but we do switch the second because we made it negative. And then we just solve each one. So like here I'll divide by 2 and x is greater than 7. And here I'll divide by 2 and x is less than negative 7. And now that we're in inequalities, now we do want to graph. And so I'd put the negative 7 on first because it's smaller, an open circle because it's not equal to on both. And then I guess the question is it an and or is it an or? And so you can always just sort of think about it like over here, x is bigger than 7. So that is this way. All the bigger numbers than 7 are that way. And then over here, x is smaller than negative 7, and all the smaller numbers are this way. And so now I can really see that this is an OR graph, but there's kind of a trick too. The original symbol that I had was greater than, and if you kind of say it long, drawn out like you're Southern, greater than, that word or kind of shows up in there if you think about it. So whenever I start with a greater than symbol, you're always going to have an or inequality. And so let's go through and try a couple more. Something like this next one is a little different. And the reason it's a little different is because all the numbers so far have been inside the bars, but this plus 5 is not. And so you actually do have to get rid of that first. So I would need to subtract the 5 on both sides, and then I'd have absolute value of x is less than or equal to negative 3. And then I would go about solving the same way. So now that my bars are alone, I'd say that x is less than or equal to negative 3. And then over here, I'm going to want to switch it and switch it. Because when I change the sign, I should switch my inequality. Now, if I think about graphing this, I think we're going to kind of have a bad time. This starts off as a less than. So if you kind of say it long drawn out like you're Southern, less than, you'd think that maybe it would be an and inequality. But this is saying that x is less than negative 3. So if we think about that this way, and x is greater than 3, I can't be less than negative 3. and greater than 3 at the same time. This is an impossibility. And the reason that I don't have any answers here, and this is like impossible, is like kind of right at the start here. We said that an absolute value was going to be less than a negative number, like be more negative, and an absolute value can't even be negative. So right off the top here, I kind of knew that there was going to be no solution. Alrighty, let's try a couple more. So again, I have something outside the bars. I want to get rid of that 1/3 first, and I can't distribute it in. We have to get rid of it. So I would multiply the 3 on both sides, and then we have absolute value of x plus 3 equals 30. Now that my bars are all alone on this side, we can make our 2 equations. So we'd have x plus 3 equals 30, and x plus 3 equals negative 30. Then we go about solving each one, so I'd subtract the 3, so x equals 27. And over here, when I subtract the 3, x equals negative 33. And these are definitely answers that I can go back in and check, but I know that they are because the absolute value is equal to a positive number, and that's fine. If this was equal to negative 30, then that would also have been no solution like the last one. So trying a couple more here. I need to get rid of this number on the outside first. I can't distribute it through, so I'm going to divide it away. And so we'll have absolute value of x minus 12 equals 7. And now that my bars are alone, we can make our 2 equations. So like x minus 12 equals 7, and x minus 12 equals negative 7. Then we solve each one. So like I'd add 12, and x equals 19. And I'd add 12 over here, and x equals 5. And notice that I didn't graph either one of these, this one or the last one, because they were equals, so not important. Okay, on this one here, I do need to get rid of the stuff outside the bars first, so I'm going to subtract the 3. And so we have absolute value of x minus 2 is less than 2. And now that my bars are alone, I can make my 2 equations. So x minus 2 is less than 2. And x minus 2 is negative 2, but because I switched the sign, I got to switch the sign. So switch and switch. Then we solve, so I'll add the 2, and x is less than 4. And I'll add the 2, and x is greater than 0. So on my graph, we got 0 and 4 open circles on both. If I go back and think about the original inequality, it's less than. So, and, which means I'm going to connect these. And the inequality shows me as well, x needs to be less than 4 and bigger than 0. So all this stuff in between. Last one, we'll add the 3 because we need to get our bars all by themselves. And now that they are, we can make our 2 equations. So 2x minus 1 is greater than or equal to 5. And 2x minus 1 is less than or equal to negative 5. And then we'll solve, so add 1. So 2x is greater than 6. And then divide 2, so x is greater than or equal to 3. And over here we'll add 1, so 2x is less than or equal to negative 4. And then divide 2, and x is less than or equal to negative 2. Now, again, if I go back to the original, this is greater. So I know this is going to be an or inequality. And if we think about negative 2, closed circle, and 3, closed circle, I can even see that here because x is going to be bigger than 3 or smaller than negative 2. All right, guys, I'll see you tomorrow for our quiz.